Hello, can you all hear me? Am I audible?
Yes, sir.
Yes, sir.
And this white screen is also visible? Hello, this whiteboard is also visible?
Yes, sir.
Okay. So what has been given in the problem is an air preheater in the form of a tube bundle is used to preheat air by heat exchange with hot flue gas. Uh, the feed air flows through the tubes and the flue is in cross flow across the bundle. There are 10 transverse rows with 12 1-inch outer diameter tubes in each row. The tubes are in staggered arrangement with a transverse pitch of 2.5 centimeter and longitudinal pitch of 3 centimeter. The upstream velocity of the flue gas is 5 meter per second and the temperature is 250 degrees Celsius. The average tube surface temperature is 120 degrees Celsius. Calculate the drop in the flue gas temperature as it leaves the bundle and the rate of heat transfer to the air. Property of the air at 250 and 210.5 are given. Okay. So what is being given here is if I have to draw a figure, maybe I'll just copy a figure from let me just copy a figure from our presentation so that we will be able to understand what we are trying to say here. Okay, so this is the figure which we have seen in our class lecture, isn't it? So what is being given in this particular problem is I will just write down the data which is being given is, so data given is so longitudinal pitch is given, that is given 3 centimeter. So this becomes 0.03 meter. Then transverse pitch is given, ST is given, so that is 0.025 meter. Correct. Now this is a staggered arrangement, isn't it? Staggered, it's already given, isn't it? Staggered, correct. Staggered arrangement of the tube is there. And how many total tubes are there? So there are 10 transverse rows. There are 10 transverse rows, means 1, 2, 3, 4, 5. In this manner, there are 10 transverse rows, and in each row there are 12 tubes are there. That is what is been given in the problem statement. If I go back at the top, that is what is been given. If you read, there are 10 transverse rows with 12 1-inch outer diameter tubes in each row. Okay, so how many tubes are there? Total are, hello, total number of tubes are, so total number of tubes are going to be 120 with outer diameter of each tube is 1 inch. So 1 inch means 0. So this is going to be 0.0254. This is what is being given. Correct. Again, the temperature here at this end, the temperature here is given, so that I will again write down. The temperature here is given as, let's say this is T1. T1 is 250 is given here. What is the temperature here is unknown, and temperature inside each of these tube, let's say, is T naught, let's say. So this T naught is given, that is the temperature of the fluid which is flowing through each tube is 120 degrees Celsius. This is what is been given. Okay. Now what we have to find out is what this temperature is going to be. That is what we have to first find out. And then the rate of heat transfer to the air we have to find out. Okay. Correct. So now okay, so now in this case, just to simplify the analysis, these are the tubes from which there is a air is flowing inside this tube, and these tubes are given in a see these, we can see the cross section of the tube. So these are in the direction perpendicular to the screen, isn't it? And the flue gas is flowing horizontally across these tubes, across the bundle of these tubes. There are 120 total tubes are there. Each tube is 1 inch outer diameter, so that becomes 0.0254 meter outer diameter, and transverse pitch and longitudinal pitch is given. The tubes are arranged in a staggered manner. That is what is been given. Inlet temperature of the flue gas is 250. Outlet temperature of the flue gas we don't know. What is the temperature of the air which is flowing through each of these tubes? That is given 120 degrees Celsius. So this is the information available with us. Okay. Now the important point to note down here is, so clearly the air is flowing across the tube. That means the forced convection is going to take place, isn't it? So whenever we are looking at the forced convection, clearly in that case we have to look at the average, fluid properties we have to look at, isn't it? So now in this case, if you look at the average fluid properties, see here the temperature is 250, but outlet temperature here is unknown. Outlet temperature here is unknown. So average temperature, uh, you know, uh, between these two ends is not known to us. Between these two ends are not known to us because the outlet temperature of the flue gas is unknown. Correct. So let us for a time being consider all our properties at 250 degrees Celsius first. Then solve the entire thing, find out the outlet temperature. Once we find out this outlet temperature, maybe I just put it T1 and T2. Let's find out the outlet temperature T2, and once we know the outlet temperature, then we can again find out the average temperature between T1 and T2 and find out the properties of the flue gas at that particular temperature and solve this entire problem again for the second iteration, and we have to continue this iteration till the outlet temperature which we have found out and the outlet temperature which is being used for calculating the properties of the flue gas becomes same. Okay, so these iterations have to be performed several times till there is a match between these two temperatures. Another important thing to note down here is again see the flue gas is there. So just to simplify our analysis, we can assume that the properties of the flue gas is same as that of the air. We don't know the composition of the flue gas, so we can make the assumption here that the properties of the flue gas are exactly same as the properties of the air. So with this assumption now our analysis can be simplified further. So I will just write down again that part here. So assumption here is assume the properties of flue gas same as air. This is the assumption. Okay, this is the first assumption. Second assumption is properties at 250 is used in first iteration. Okay, so let us do the calculation of the outlet temperature, and we will continue this iteration till the outlet temperature obtained and the outlet temperature used for calculating the average value is same. So in the first iteration, iteration 1, the average temperature is 250 degrees Celsius. That is what is assumed. That is what is been assumed. Average temperature is 250. Average temperature of flue gas. Because this T2 is unknown, that is why we are starting with 250 degrees Celsius itself. And based on this, we will find out T2. And then again, we will take the average temperature and find out the outlet temperature and see whether there is a mismatch or not. Okay. So since this is a staggered arrangement, first we have to find out what will be the diagonal pitch. So SD is the diagonal pitch which can be given in this case as, just by looking at the geometry itself, we can say this as, this is SL square plus 1/4 ST square, isn't it? So we will get this as, so SL is 0.03 square plus 1/4. ST is 0.025 square so this becomes 0.0325 meter. Okay. Now the second thing what we have to do is, first we have found out the diagonal pitch, and based on that now we have to find out the maximum velocity, because if you remember the last class, whenever we look at the heat transfer across the bundle of the tubes, we look at the maximum velocity for calculation of the Reynolds number. So Vmax in this case can be given as, this we have already seen in the last slide. So velocity is already given, so we can write down everything here. 0.025 divided by 2. SD is we have just obtained 0.0325 minus diameter of the tube is, each of the tube is 0.0254 into velocity is 5. So this comes out to be, anybody? Hello, calculate the value. Hello, please calculate the value.
8.8.
So this comes around 8.803 meter per second. Correct. Okay. So now we can go ahead with this. Now the properties are also given. So properties we can assume as same as that of the air. So rho is 0.666 kg per meter cube. Mu is given as 2.8 into 10 raised to power minus 5 kg per meter second. K is given as 0.042 watt per meter square. Degree Celsius, and Prandtl number is given as 0.683. Just let me just check whether these properties are correct. Okay. So now with this we can find out the Reynolds number. So RED max, that is what we have defined, maximum the Reynolds number based on the Vmax. So that becomes dV max rho by mu. We can put all the values here, so that becomes 0.0254 into Vmax is 8.803 into rho is 0.666 divided by 2.8 into 10 raised to power minus 5. Okay. Now, once we know the maximum Reynolds number, what is the value? Anybody got the value?
5318.4.
5318.4. This is the Reynolds number. Okay. Now, once we know this, now after that, what we have to do is we have to find out the constants, and I'll just show you I will just project the class note so that you all will be able to see. So this was the example, isn't it? So first, is the slides are visible? Hello? Is the
Yes,
slides
sir.
are visible? Okay. So the next step is first we have to find out Vmax. Once we know the Vmax, then we have to find out the Reynolds number. And once we know the Reynolds number, based on the value of the Reynolds number and value of ST by SL, we can find out the constant C and M. That is what we have to do. Once we get C and M, then we can use the equation, this equation, and find out the Nusselt number. Okay, so I'm going to do the same thing based on the values given in this table. Okay, so I'll just project again the same file. So now in this case, ST by SL is 0.025 divided by 0.03. So that is definitely less than 2. And corresponding to this Reynolds number, from the table, find out C. C is given as 0.35 into 0.025 by 0.03 raised to the power 0.2. So this comes out to be something, and M is given as 0.6. Okay, so find out C. So constant C in this case comes out to be 0.337. Is it correct? So now we can use the expression of the Nusselt number. So Nusselt number in this case is given as 0.337 into Reynolds number raised to the power 0.6 into Prandtl number raised to the power 0.36 into the viscosity ratio is there, mu by mu w is there, so that we can assume Prandtl number by Prandtl number at the wall is given, so that we can assume equals to 1. So this is just 1. Okay. So 0.337 into Reynolds number is 5318.4 raised to power 0.6 into Prandtl number is 0.683 raised to the power 0.36 into 1. Calculate the value.
$50.52.
Correct. So based on that, now we can find out the heat transfer coefficient. So this is HD by K, HD by K. So H we can find out 50.5 into K multiplied by K. So K is already given. So K is 0.042 divided by diameter. So 0.0254. So this comes around 83.6 watt per meter square degree Celsius. Is it correct? Hello?
It's coming out to be 83.5.
Now what we have to see is based on that. Now we have got the heat transfer coefficient. Ultimately what we are interested in, we are interested in the what is the outlet temperature, isn't it? Outlet temperature we wanted to find out. We can make the balance in this case like this. So whatever the heat lost by the hot fluid should be whatever is the heat transferred from the hot fluid to the fluid which is flowing through the tubes, isn't it? So the heat transfer to the fluid which is flowing through the tubes can be given as HA delta T LMTD, isn't it? Because the temperature difference is varying as we move along, isn't it? Whereas whatever the heat lost by the hot fluid, that is the flue gas, can be given as MCPDT, isn't it? So that balance we can make it here. But here we know only velocity, we know the density, we don't know what is the mass flow rate, that we don't know. Okay, so we can calculate that based on the cross sectional area and other things given. Okay, so let us find out. So cross sectional area. So if I go back, maybe I'll just go back to explain this further. What I'm trying to say is, we wanted to find out what will be the cross sectional area here. We already know the velocity here, that is 5 meter per second is already given. If you know the cross sectional area multiplied by the velocity, that will give me the volumetric flow rate, and volumetric flow rate multiplied by density is going to give me mass flow rate, and then I can directly apply MCP/dT and find out what is the heat lost by the flue gas, and that I can equate to HA delta T LMTD, because in this case why LMTD, because the temperature difference between the hot fluid and the cold fluid here is going to be 250 minus 120 at this end. But as I go along the bundle of the tube here, the outlet temperature of the flue gas is going to be lower, isn't it? It will not be 250 degrees Celsius, even though the temperature of the cold fluid, which is cold air which is flowing through this tube, is constant to 120, but there will be definitely a temperature drop in this T2, isn't it? So T2 is going to be lower than 250. That means the temperature difference between the hot and cold fluid at this location and at this another location is going to be different, and it is reducing as we are moving, and therefore we have to use log mean temperature difference here. Okay, clear? So that is what we are going to do one by one here. So we have obtained the heat transfer coefficient. Let's find out the cross sectional area. Cross sectional area for flow, isn't it? So now cross sectional area for the flow will be what? Remember, what is the length of the tube? Length of the tube is given as 1 meter. Length of the tube is 1 meter, and the transverse pitch is given. So transverse pitch, if I look at carefully, if I look at, if I again go back, so transverse in a given transverse pitch, there are 2 rows of the tubes are there, isn't it? And how many rows are there in the transverse direction? There are 10 rows are there, isn't it? So that means how many, if I have to find out the cross sectional area, that means the length of the tube, that is 1 meter into there are 5 such transverse rows will be there. There are 10 rows, but these 2 rows are basically accompanied by 1 transverse pitch, isn't it? So this transverse pitch is accounting 2 rows, isn't it, in between? Correct. So that means what? That means what? We have to multiply the transverse pitch divided by 2 into total number of rows into the length of each tube, that is going to give me the cross sectional area. So let us calculate the cross sectional area for the flow. So that can be given as.
So can you repeat again from the diagram?
I will again go back to the same figure. I just wanted to ask a very simple question. What will be the cross sectional area if I look at this direction, the direction of the flow? What will be the cross sectional area? Remember, the direction in the Z direction, the length is 1 meter because the length of the tube is 1 meter, correct? And now I wanted to find out what will be the height from bottom to top, isn't it? There are 10 transverse rows, and between these, see, between 1, 2 and 3, what is the transverse pitch is there? That is given as 0.254. 0.025 is given, isn't it, meter? So that means how, even though there are 10 rows, but actually if I look at the transverse pitch, it accounts the 2 rows in between, isn't it? So that means what? Half of the transverse pitch multiplied by total number of rows in the transverse direction into the length in the Z direction, that is going to give me the cross sectional area. Is it right?
Yes, sir.
So this becomes, so transverse pitch is already given, that is 0.025 divided by 2 multiplied by 10 rows are there, isn't it? And multiplied by length of each tube is 1. So this becomes anybody?
0.125.
0.125 meter square. Now we have to find out the volumetric flow rate. So volumetric flow rate is going to be what? Volumetric flow rate in this case is going to be what? This cross sectional area multiplied by velocity. So 0.125 into 5. So that is going to be my volumetric flow rate, isn't it? And what will be mass flow rate? Mass flow rate is going to be 0.625 into density. So density is given as 0.666. So this becomes 0.41625 kg per second. Is it right? Is it correct? Now let us make a complete balance here. Let us make a complete balance. So complete balance in this case is what? MCP/dt, isn't it? So MCP/dt is MCP T1 minus T2, isn't it? So this is nothing but the heat lost by the flue gas, and that should be same as H into area. Let me write it AH. So this is heat transfer area, AH into delta T LMTD. So this can be written as, maybe I'll just write down here. So 0.416, 416, let's put it. CP is given as CP, the value of specific heat in this case given as 1035. Temperature T1 is given as 250. 250 minus T2 is unknown. T2 is unknown. H we have already calculated earlier, so that value is 83.6, isn't it? What will be area? Heat transfer area. Now heat transfer is taking place over the entire bundle of the tube, isn't it? What is the area of each tube? Area of each tube is going to be pi dl, isn't it? And pi dl multiplied by total number of tubes, that is going to be give me the total heat transfer area. So pi in this case is pi into dl is 0.0254, because diameter is this 0.0254 into length of the tube is just 1 meter, isn't it? And how many tubes are there? There are 120 tubes are there. So this is going to be my heat transfer area. What will be delta T LMTD? If I look at the end here at this location in the left hand side, the temperature difference is going to be 250 minus 120, whereas on the other side the temperature difference is going to be T2 minus 120, isn't it? So that we can put it in finding the LMTD. So here the first temperature difference is going to be 120 minus, sorry, 250 minus 120. 250 minus 120. This is the first temperature difference. Second temperature difference is going to be what? T2 minus 120. T2 minus 120 and divided by ln of 250 minus 120 divided by T2 minus 120. So this is what is going to be there. Now, if I look at this particular thing, this is nothing but what? This 120 will get cancelled out. So this is nothing but 250 minus T2. This is what I am going to have. And this get cancelled out with this. This get cancelled out with this. So if I rearrange everything, what I'm going to get here is, if I rearrange everything, so ln, basically what I am supposed to get here is, if I rearrange everything, is ln 130 divided by, so this 250 minus 120 is 130 divided by T2 minus 120, and that should be equals to equals to 1.858. Just check whether this is same. Check whether this is correct or not. Hello. Can you please check the calculations whether these are correct?
Yes, sir.
Yes, sir. So now there is no trial and error. We can rearrange this and find out T2 from this. So T2 comes around. Anybody? So this will be exponential of this answer multiplied by and this inverse into 130 plus 120.
231.8.
Around 140 I am getting. Just check whether it is correct. Just check.
Yes, sir. 140.27.
So 140.3185 is what we are going to get it. Okay, now so now based on this, now clearly the outlet temperature is 140.27. But remember, when we started solving this particular problem, what we have assumed that the T2 is also 250. That is why the average temperature we have used as 250 and found out the properties at that particular temperature. Correct? Isn't it? That means our starting assumption was not correct, and therefore we have to go for a second iteration. So iteration number 2 we have to do, isn't it? So iteration number 2. Now what we have to do is, first we have to find out average temperature. So average temperature in this case is going to be what? 250 plus 140.27 divided by 2. So that comes out to be around 195.159. Okay, correct? That is what we are assuming. That is what we have obtained, isn't it? So now all our properties, remember all our properties we have found out at 250 degrees Celsius. That is what has been given. Now we have to find out the properties at 195.159 degrees Celsius, isn't it? So I can give you the properties at this particular temperature. So that can be given as so let me check what properties I have given at 210. So 210.5 I have given, so that is I will just remodify a little bit. There's some mistake was there. So let us have the new properties. So rho at this temperature is going to be 0.76 kg per meter cube. Mu is given as 2.507 into 10 raised to power minus 5 kg per ms. Okay. Cp is given as 1023 joule per kg per degree Celsius. Prandtl number is given as 0.686 and K is given as 0.0379 watt per meter degree Celsius. So these are the properties which I have taken from the back side of the table. I will correct it in my answers also. Okay. So now all the calculations which we have done with the properties at 120, now we have to repeat it for this, and we have to go till our temperature matches with the outlet temperature. Okay, so let us go ahead with this. So the first correction what we have to do is the velocity v is given as 5 into 5 meter per second is given, isn't it? So that is at the average temperature of 5 meter per second we have taken, isn't it? So this velocity v equals to 5 meter per second we have taken, and remember this is the average velocity we have taken, isn't it? Even across the bank of the tubes at that particular temperature. But now the temperature is changed from 250 to 195.159, and therefore this velocity is also going to change. So this velocity will be given as, so new velocity will be given as, in this case I will just multiply this as 195.159 plus 273 divided by 250 plus 273. So this is directly coming from the ideal gas. This what will be the new velocity that I am directly calculating from the ideal gas. So if you look at the relationship between this velocity here and, so I will just do it here so that you all will be able to understand. So m dot is nothing but rho into v, isn't it? So rho in this case is going mp by nRT into v. So from ideal gas, mp nRT1 v1 should be mp nRT2 v2. So this is volume, and based on this v1 by t1 should be same as v2 by t2. So this v1 is nothing but volume, so that can be represented as au1 divided by t1 equals to au2 divided by t2. So that means based on this we can directly write down u1 by t1 is same as u2 by t2, and now we wanted to find out u2, isn't it? This is volume. So these are volume. This v is not velocity, this is volume. Okay. So here maybe I'll just do it carefully so that there should not be any okay. So now it looks okay. So this will be T1, T2, T2, V1, V2, V1 T1, V2 T2. Okay. So this is what is going to be the relation here in this case. Okay. So from this we can find out the new velocity that comes out to be 5 into 195.159 plus 273 is 468 divided by 250 plus 273 into 5. So this becomes 4.475 meter per second. Okay, so now again we have to do all the calculation with these new values. So let us calculate Vmax. Let us calculate Vmax. So Vmax comes out to be 0.025 divided by 2 into 0.0325 minus 0.0254 into 4.475. So Vmax comes out to be in this case is, anybody please give me the values.
7.8.
7.8. Okay, I'll just write down that 7.8 meter per second. Okay, and then we can find out Nusselt number. So Nusselt number in this case will be given as 0.337 into, okay, Reynolds number RED max will be, calculate the RED max. So that will be 7.8 into 0.0254 dV into rho. Rho in this case is going to be 0.7. I have given the value 76 by mu. Mu is 2.507 into 10 raised to power minus 5. So this comes around, maximum Reynolds number comes around 0.0254 into 0.76 divided by 2.507 into, so this comes around 6006.03. So this comes around 6006.6 into Prandtl number is 0.686 raised to the power 0.36 into 1. So this comes around, is it correct? Is it correct? Into the thermal conductivity is taken as 0.0379 divided by the diameter, so that becomes 0.0254. So it becomes, just check whether these values are correct. So this comes around 81.02 watt per meter square degree Celsius. Is it correct? Hello, anybody? Anybody got the values?
Yes, sir.
Yes.
So now everything we know, now we can make a balance again for the new condition. So the new condition, for the new condition, again the balance becomes, if I go back, so the balance in this case, again let me just go up. So mass flow rate we have already calculated, that is 0.416. So I can again make 0.416 into CP. CP value is 1023. So
Excuse me, sir.
Yes, please go ahead.
Sir, in
Please go
mass
ahead.
flow rate, we use the previous value of density.
Mass flow rate.
For calculating mass flow rate, we use 0.66 as density.
Yes, yes.
So
Just wait.
we have to calculate it again, right?
So calculate the mass flow rate here. So basically in this particular equation, if you look at mass flow rate, we are equating, we are keeping the mass flow rate same. This calculation, if you look at this, that is why we have changed the velocity here. We have kept the mass flow rate same. Remember this, we have equating, isn't it? Hello? So if you look at the change in the velocity into the mass, the density, if you do, mass flow rate will come out to be the same. So this is going to be the same, doesn't matter. Okay.
Okay.
So this will be 250 minus T, and again the right hand side will be HA delta T LMTD. So 81.02 into area is going to be pi into 0.0254 into 1 pi dl into 120 multiplied by 250 minus T divided by ln. 250 minus, sorry, 120 divided by T minus 120. Okay, so rearrange the equation and find out. This is going to get cancelled out again. This will get cancelled out. So find out what you are going to get it. So 0.0416 into 0.416 into 1023 multiplied by 81.02 multiplied by 3.14 multiplied by 0.0254 into 120. So what you are expected to get here is ln 130 divided by t minus 120 is going to be 1.822. Correct? So from this you back calculate the value of t. So (130) plus 120. So this comes around 141.01. So now we don't require additional iteration is not required. Additional iteration is not required because the earlier temperature assumed was earlier outlet temperature for calculating the average value. Remember, here we have calculated the average value. That is that temperature we have assumed is 140.27. So this 140.27 and the obtained temperature of 141.01, this is very close, isn't it? So no further iteration is required. Is it all right? Correct? Are you all able to get it? Hello? Hello?
Yes, sir.
So now this is part A. Now let's look at part B. In part B, we just have to calculate rate of heat transfer. Okay, so rate of heat transfer is obtained as MCP dt, so we can directly do 0.416 into 1023 into 250 minus this outlet temperature 141.01. Or we can take the average value, so that comes around, it's perfectly all right even if we take this, so doesn't matter. So this comes around I think 46378.5 watt. Is it correct? Is it correct, guys?
Yes, sir.
So this is the end of the problem. So we stop here unless you have any doubt, any questions to ask. If you have any questions, then I will be happy to answer. Otherwise, we'll wind up.
Sir, in option A, if we have to take another iteration, then how we will calculate average temperature again?
In option A, suppose this temperature, yes, okay, let me just explain you. Suppose this temperature 141 is not close to the early, let's say instead of 141 we got 120 here. Okay.
Okay, sir.
So what we will do now, we will take 120 plus 250 and we will take the average of that, and we will again go for one more iteration with the new values of the parameter. Suppose this we would have got 120. So then in the third iteration, what we would have done is we would have just went ahead here with the new temperature. The new temperature is, let's say, 120. So 250 plus 120 divided by 2, we would have got the new value of the average temperature. We would have found out all the properties at the new value of the temperature and then solved. And this iteration we would have continued till this temperature used in calculating the average temperature and the obtained outlet temperature is coming very close to each other.
Okay, sir. Thank you, sir.
Okay.
Sir, how much is allowed for the?
Your voice is not clear. Can you please repeat?
Sir, how much error percentage is allowed while checking whether the temperature is close?
If it is 1 or 2 degrees, then it's perfectly all right. Even if such question, if I ask in the examination, I will not mention that it should be matching with the final temperature. I will only say that you perform the calculation for 2 iteration, 1 iteration, 3 iteration, something like that, isn't it? Because you never know how many iteration it requires. Correct? If that is what the question is. In real life, in an industry, if you wanted to do it, then you have to do as many iteration till it matches close to your tolerance limit. Is it okay? Hello? Hello? Are you able to get it what I'm trying to say? Hello?
Yes, sir.
Okay. Any
Yes,
more
sir.
question? Yes, please go ahead. Any other question, friends? Okay, so if there is no question, we stop here and see you on Thursday. Okay?
Yes, sir, sure. Thank you.
Thank you so much.